well, while you were out having fun, somebody insisted I explain this. And so we had this before people left the room. And what you can do is you can take this, as I've said, in words, but felt too lazy to write down. I could take it and write this as mine is a half F star, mine is a half F star. 1/2 plus 1/2 equals 1. Still, that's still true. You know? And then under that coercive condition, the set in which this is positive is a finite set. You know, this thing blows up when x or y gets large. So the set in which this thing in parentheses is non-negative is a finite set under that coercive business. Okay, and I just wrote that as S.
That's an inequality?
It's an inequality because I basically just S is a set in which this is greater equal to 0. You know, and so when it's negative, I just say, oh, forget it. I'll just, you know, and that's why I have an inequality. And I realized that here I don't need the half because F star is greater equal to 2 because it's the sum of two F's. So I divide by a half, I get something greater equal to 1. So I get to erase my 2 over here. The 2 is going to pop up again in a second. You can get rid of the 2. I mean, the 2 is fine. You can keep it. All right. Okay.
I'm still a little confused about this motivation if you want to study X compared to Y.
Well, yeah, you'll see it though. I mean, we're going to use it a lot. Like I gave you one motivation. If Y was stationary, then we've got an ergodic theorem. The expectation of f of y of t doesn't depend on time, and so that's ergodic theorem will hold for X because X and Y couple. And we'll do that next lecture. I was struggling with which example I should give first. I'm going to do value iteration now and ergodic theorems next time.
So any conclusions you make on Y, why can't you just directly apply them to X if they have the same transition matrix?
No, I just gave you an example. I mean, if Y is stationary, right, there's an example. So if Y were stationary, then the average cost would be pi of c for all time. That's an awesome ergodic theorem. You know, it's better than geometric convergence you saw in the homework. It's instant convergence. Well, if I start with a different initial condition, to use this, coupling will be a way to use that. You know, you know. The fact that I can actually guarantee that x of t equals y of t, I have to find, and that's a fun thing to think about. A Markov chain, you know, you can think of a Markov chain that after some random time is stationary. You know, it's not approaching stationary. It bounces around and suddenly gets to latch on to a stationary process. That's pretty wild. I mean, it's not the way you usually think of things. You know, you usually think about, like, especially if you've been raised in control, where you reach an asymptotic limit point and you never get there. You get out, you converge asymptotically quickly. Here, you bounce around and whack, I'm stationary. I'm in steady state. You have to after t. It's a weird way to think about things, you know. And but this is just one realization. I mean, it's yeah. All right. So a stronger conclusion does have a 2 in there. Excuse me. Oh, I guess I wrote it in. So really the conclusion was this. We said last time, if that condition V3 holds, then that's my f star, satisfies a bound. But that half here is what screws me up. So I'd have a half here, and I'd have to bring it to the right-hand side. You know? Yeah. So that's where that 2 really comes from. And this is what we'll put to the use today and next time. You know? That the cost till they couple is bounded. All right. All right, shall we? Value iteration. I just want to say a few things about it. Partly it's used a lot for computation. Partly it is a beautiful tool for illustrating some of the concepts we've used. You know, so for both reasons I'm covering this. So basically what it is we'd like, I mean, right now it's going to be to solve Poisson's equation, to compute the solution to Poisson's equation. Okay. As I said, if you have a finite state space Markov chain, this is typically a stupid way to do it, but it has broader implications, and it's a good way of, you know, it's useful for other reasons. So here's the algorithm. Okay, so I'm given an initial function in a v0. It's some guess as to what h looks like. And for each n greater equal to 0, I update. There's the algorithm. So you can see why people like it. You can code this in 2 lines. But the inverse you can code in 3 lines, so it's not that big a deal. And let's write that out. What I mean is Vn plus 1 of x equals C of x plus the summation of x prime so that's what I mean, right? And so V is a function, but again, you know, the reason I think of it as a vector is because that looks like matrix vector multiplication. This is something you're going to have to memorize. And that's part of the reason I'm doing this as well. I want you to memorize this idea that conditional expectations are matrix vector multiplication. Right? So that doesn't look anything like this, does it? I mean, it's really, there's a tilde there and there's no tilde there. It's quite strange. So why on earth could these be related? Well, let's try to understand this. What we're going to show is remember h was called a relative value function. Well, it's the relative cost that converges. So basically, look at this function at stage n of the algorithm. You subtract off the value at one particular point, and that's going to converge to a solution to Poisson's equation. But this is not unique. I can always add a constant and get a new solution. But it'll be the unique solution satisfying h of x star equals 0. Because after all, if I plug in x star, I get 0. So we might as well give that a name. You know, just call that hn of x. It's our candidate approximation at stage n. Okay. Now that's not really where this is usually used for. this is like not is, but this is a building block of what's called model predictive control. Because it turns out that to be shown, fact, if you look at this function Vn of x, it is just a finite horizon cost. So this initialization of value iteration is actually the terminal cost, in the typical setup for model, what's called model predictive control, which we'll come back to later. And you prove this by induction. It's trivial to substitute, but let's do it. Yeah. So that's a standard objective when we have a control problem, is we'd like to minimize some finite horizon cost over all policies as a standard thing, and it's the basis of what's called model predictive control, which we'll come back to. Okay, that to be seen. And one thing really valuable I want to sink in is that the choice of V0 is important. Choosing a V0 that fits the structure of the model can really make a huge difference in that particular application. And let me explain that, if I can. You with me? First, let's prove it. Or you do it. So get out your pens, write down the proof. After all, we know what Vn plus 1 is in terms of Vn, and we know how Vn is related to Vn minus 1. Do it, all of you. Don't make me do it. Would somebody like to volunteer and do it on the board? We won't laugh at you. Jonathan? No? No? You want to? Oh, have you got it written down first?
I haven't written down.
Oh, no.
I see what it is.
Yeah, okay, well, go for it. Yeah, Jonathan's always a brave soul.
I think I see what it is.
Yeah. And then we promise not to laugh.
Okay. Which is equal to C plus the expected value of V n, given Vn minus 1, or no, I'm getting myself mixed up.
Oh, no, it's easier than that. I think it might be easier than you think.
Oh.
Oh, it's like a one-liner almost. What's Vn minus 1?
Right. Okay. Yeah, that was my plan to start with, and then I got all that. Yeah. Vn minus 1, and then that's equal to C plus P, C plus V, P, V, n minus 2. And then so on and so this is, so that's 2C plus, or is
what does Trump hate?
Everything.
PC.
PC plus p squared v n minus 2, and Yeah, and then PC is the expected value. Yeah. Okay, but how does this one get in?
Keep going. You have to. You start with the big N, so you have to do this like more times.
Plus P squared C plus P V n minus 3 equals C plus P C plus P squared C plus P cubed V n minus 3.
And now let's take n equals 3.
Okay.
Are we done? Yeah, n equals 3, we're done. So that's different, n equals 3.
Okay.
Yeah, I'm going to take over. Awesome, thank you. It's because the thing is that the first thing to do is to remember that this expectation starting at x is just p to the. I can take the sum outside, This is just equal to the sum t equals 0 to n minus 1 of p to the tc at x plus p to the n v0 of x. This and this is the same thing, right? The expectation of v0 of xn is this p to the n v0 and then evaluated at x. And so you can see a proof here for n equals 3, but it's just by, you can say it's by induction, but it's also just by, forget induction, it's just by substitution, because you could just go and see it. Although, let's be precise, it is an inductive proof no matter what. So that's good enough, that's what I'll take it. So, So before showing this converges, I want to show you a really cute fact. So this is why I make a special structure. Now again, this would be just in a finite state space. You'd say, well, Jesus, I can always just take v0 equals 1, and I'll take eta bar 0 to some huge constant. Now, the point here is we're trying to get bounds. So we want to do this so that eta bar 0 is as small as you can manage. You've got some insight, you've got something, and the state space might be billions or something. It might be huge, but you've got some structure. And throughout the course, I'll give you examples where you can get a lot of structure, and so you can choose v0. If you are clever and can find us a initialization like that, then the same thing holds for every n. And actually, I don't think, do I want to call that? No, forget the 0. Erase that 0. Then the same thing is true for every n. And in fact, there's a decreasing sequence, or non-increasing. So basically, every PN, if you start with the Lyapunov function, every value function is a Lyapunov function, and satisfies the same, same sort of style, but the bound on the average cost gets better and better and better. So there's a monotonicity, which is awesome. And it's good for, if you were in a countable state space, this would be great for stability. It's stable. If you start off with if you choose go back to MPC. If you choose your terminal cost function as a Lyapunov function, then every single guy you get is a Lyapunov function. And again, we'll see that's huge impact for control. So people say, MPC is not stable, it's so hard to use. We'll say that's nonsense. It's just a matter of initialization. It's trivial to make it stable, and this is the tool. Okay, so how do you prove this? I've never had time to make this proof more elegant. And every time I've taught this, I think I want to go back and make it prettier. And let's try right now.
So you choose a V naught, and then where does your V
We'll do evaluation right there. Yeah. So we're trying to analyze. We're trying to analyze this algorithm, and there's a short proof of this fact here, but I know that there's some insight that's missing. I'm not sure what it is. So what you do is you do this though. Where do I define this? I guess I can get rid of this. All that burn in these skulls. Yeah. Yeah, so they're monotone decreasing. I think you can prove they're strictly decreasing. If they're ever equal, then you've actually solved Poisson's equation, which is impossible. I think you can prove that as well. Conjecture, I think I proved that once, but I think they're strictly. I think you'll see the proof right now. So how do you do this? Well, it's sitting in our faces, isn't it? There's the algorithm. It's the only thing we have to work with. How could this look anything like that? What we're going to do, we're going to put that there. And I'll get an equality first. I've got an equality there, I've got an equality there. That's equal to Vn minus C. So PVn, I've got minus C. But I wrote Vn there, that's a mistake, right? What's a mistake? Yeah, that's wrong, damn. Is that what I did? That's my notation, right? Yes, so if value iteration is equivalent to this very, very seductive looking formula, where Gn is the difference, then all I'm saying obviously is that I need an upper bound on Gn, which is decreasing. Okay, and so basically that's it. And so let's show the GNs are bounded so eta bar n is going to be the maximum of this over all x. And let's show those guys are decreasing. And how do you do that, everybody? You write down Gn equals Vn plus 1 minus Vn. And if I'm going to make these guys decreasing, I've got to somehow relate Gn with Gn minus 1. or Gn plus 1 or something. And I guess, and that's what I mean about my notes being something screwy. They seem like they should be much simpler. So first I'm substituting Vn plus 1 is C plus PVn. That doesn't look very useful. But then I say, well, Vn itself is something similar. And that's starting to look suggestive, right? So I did it twice. I said Vn plus 1 is that, and Vn is that. And you do this, you see the C's cancel out, and what am I left with?
Negative PG.
Yeah, PG, blah. There's Gn. It looks like I've got P times Vn minus 1. So it's exactly P times G n minus 1. And the transition matrix is a contraction. You know that's a conditional mean. So, and so there you have it. So this is a function of x, but it's a conditional expectation of g of n minus 1. So it's got to be less than or equal to its max, which is defined to be eta bar n minus 1. Okay? So I've got a uniform bound on Gn, and now I can take the max over all x on the left-hand side, and I'm done. Well, we can go through and let's be explicit about it. Yeah, absolutely. What you said is absolutely true. I mean, P Gn minus 1. I left out the x's, but who cares? Now that is less than, it's the linearity of the expectation. This is less than or equal to its max, and then I get a constant. So if I've got a function which is less than or equal to another function, the expectations are monotone. It's linearity there, and that's a constant. So. So QED, that's it. So it just comes out. You know what I mean? There's something deeper here. I just don't like this proof. There's a meaning here that's lost, and I don't know what it is. But anyway, it's good enough. I feel like I've never had time to sit back and see if there's another interpretation of what's going on here. All right. You with me? So, yeah, we're not, I don't know. We should open those doors again. It was ingenious to have them open. Do you mind? It's stuffy in here. All right. So, all right. So there it is. So again, there's a QED symbol right there. And so we'll come back to this. The same idea comes in the controlled context, and it tells you again. If you apply model predictive control, it tells you how to do it. Because the exact same conclusion will come up. And so what we'll find is that this myth that MPC is not stable is nonsense. Okay? So we'll learn that in a few weeks. Because this is an uncontrolled model, but the same conclusion in a stronger form holds for controlled Markov chains as well. And in the controlled case, it's really cool. You just need this for one policy. So for one crappy policy, as long as you have one stabilizing policy, and you initialize with that, you have stability of all the remaining policies. So, again, to be seen. Is this crystal clear? All right. So now we want to prove convergence. We're going to take the value function at stage n evaluated at x, subtract off the value, it's the value at x star, look at the relative, total cost, and then see what happens. That was my definition. No, take a look at it, see right there. So if I'm making this claim, then clearly what I'm saying is that the minimal eta bar is going to be the max of that. And I'm just taking that definition. So yes, there's a definition, right? That's a definition, and that's a definition. Yeah. And it's incredibly trivial proof. There's just nothing to it. Yeah. And again, in applications, you'll find this can make amazing differences. Anyway, go from that. So everybody tell me, how am I going to prove that HN converges? We got the big hammer we constructed a little while ago. So what's X and what's Y if I'm going to apply my coupling tricks? All right, come on.
X would be eta of X.
Yeah, in terms of starting points. Yeah. So I'm going to take it's much easier to M of t rather than indicate a function. So M of t, I'm just using M of t for this indicator function we had before. So we start off with these two guys, x of t, y of t, independent of each other initially, sort of. One initialized at x, one initialized at x star. And we go through and we use this representation that we have here. So what is Hn of x? Oh, stop, reset. All right, I haven't done anything, all right? Nothing. That's a fact. I know that Vn of x, you run the Markov chain starting at x, up to n minus 1, count up the costs up to then, take the expectation. You've got a terminal cost, you've got to take the expectation of that as well. I know what Vn of x star is. It's exactly the same thing, but I initialize at x star. So I'm just rewriting what I wrote down before. I'm just doing it twice. So I'm completely wasting chalk. But the beauty is that now I've got sample paths, and I have this very special realization where these sums that are blowing up, that's going to infinity, that's going to infinity, but they don't because eventually x of t equals y of t. So that's the beauty of these constructions. So it's really not that. Well, let's save this. So there's an annoying term in the beginning. All right, almost there. So now I want to prove a limit. Well, I've got the limit. So I let n go to infinity. Now let's just stay in a finite state space. I'll have to, otherwise I'd have to give conditions under which this goes to 0. Okay, so in a finite state space, that's a bounded thing. We just said that goes to 0. So that, goes to 0. Dominant convergence theorem, whatever you like. Right. And then as n goes to infinity here, I just end up summing up to t minus 1. So if I take the limit as xn goes to infinity of hn of x, it looks like I pulled a fast one on you. I had a y here, and why am I calling it x? It's because I changed the expectation. I'm just saying this is really y, because I'm initializing with x star. Y is just a realization of the Markov chain. It was specially constructed, but still just one example of a realization of the Markov chain evaluated x star. So putting the y there or calling it x, it's the same thing. All right. And what do you get out of this? What you find out is something awesome, is that t is a hitting timed x star. It's not the first hitting timed x star, but it's a hitting timed x star. And you get a wonderful fact that this is equal to this minus, so a Kac theorem result. So Kack's theorem said that if you took t to be the first return time to x star, then this would be true. But it turns out it doesn't matter which return time it is. It could be the second return time to x star, or this weird randomized crazy one, as long as it's some return time to x star. And it follows from the ergodic theory of Markov chains. Maybe I'll give it to you as a homework problem. I don't know. But this is really nothing, the fact that this equals this. It's nothing, and we have this as well. So, but those times are the same. So I really should go back to my original probability space. That random time there and that random time there are the same thing. I can pull this back in. Okay, I warned you, whenever I write a tilde, I mean I'm normalizing it so it has mean 0. And I get from here to there, and that looks like our old friend. Yeah, almost.
Just where the zeta times
Well, no, here,
is that equal to?
no, wait. This and this are identical because these guys couple. So after, from capital T onwards, x and t and y t are the same thing. From here to here. The fact that that's equal to that, just remember that these two guys are the same after they couple, was the definition of coupling. So I'm just emphasizing that here. I don't need that there, but I'm just emphasizing this is 0 if, oh, that should be, oh, I see. Yeah, that's right. Yeah. I mean, yeah.
So is that minus?
Yeah, that's fine. What's that? Where?
It's a minus.
Yeah, I have minus sign here. I just collected terms here. So I just didn't want to have to write down this whole thing. There's just a ditto sign there. So this is not changing, but there's a generalization of Kack's theorem that says if I start at a point and I look at some stopping time, which is the time to return to that point, it doesn't have to be the first return time. It just turns out it's a very simple generalization. This turns out to be that.
That's right.
Yeah, and so we prove this with t equal the first return time to x star. This capital T just happens to be some return time to x star. Some time I visit x star.
What happens to the first term?
Yeah.
Oh, I said, let's assume v is bounded. We know that t is almost surely, it has a finite mean. So this goes to 0, and then goes to infinity. So this whole term disappears. Well, in the notes I said, let's assume it's 0 for simplicity. But I hate doing that because it's a bad choice. It's better to choose v0 to be nice. Okay, so that goes to 0. And here this, and in the end we just n equals t. Just substituting. Yep. You first.
What specifically is eta here? It's the value of the.
Oh, eta was pi of c. The same, yeah. We started with that somewhere. We're talking about Poisson's equation. Yeah, so that's what Kack's theorem says. It relates cost over cycle to the average cost in the infinite horizon.
So it's not pi at a particular, it's not pi
No.
at x star, it's pi.
No. Oh, no, this is the expectation of this hitting time. I mean, I should get rid of the x star. It's really confusing. T was defined in this probability space I constructed. It was defined, involved a Markov chain like that, and it doesn't just depend on x star. It depends on the fact that I started not coupled, and x of t was a little x, and y of t is at x star. So that subscript there is a bit confusing. T was the first coupling time, and the first time that the two guys hit x star. And so, again, like I said here, that's a generalization of Kack's theorem. I'm not proving it, though you really could. You might not know it yet, but you could. This is also a solution to Poisson's equation. I'm summing from 0 up until a time I hit x star. Capital T is a stopping time for this bigger process. And this turns out to be a solution.
So the first term goes away because the indicator function is 0?
N goes to infinity.
So then that would be 0 then?
Well, I mean, eventually it's 0. This converges. This is it for every omega. If we look at random variables, this is eventually 0. Because T is a finite random variable. Capital T with a coupling time. So capital T for one realization of the process might be 100. Well, take n equals 101. That's 0. So T is a random time. And this goes to 0 with probability 1. Let's assume these guys are bounded. Let's stick to a finite state space just for now. All right. So that goes to 0. N goes to infinity.
Okay, the same argument as
Yeah, as n goes to infinity, I'm pinning this. I'm only counting up, summing up for n less than t because the terms are 0. The upper terms, the remaining terms are 0 once x of t and y of t are the same. And so as n goes to infinity, yeah, basically this disappears and I can replace a little n by t, by capital T. Yeah, so it's cute. And this. I mean, I'll put it in words, but that is a solution. It's the same. I mean, it is a solution satisfying x star equals 0. Yeah, and that's it. I mean, again, a couple of steps are missing, but they're algebraic, annoying pieces.
Once you have, since you have eta times the expected value of t, when you bring it in to the summation, which you have like an extra.
No, that's the fun thing. I'll write it out again if you like. Maybe that's a more elegant way of saying it. And these are annoying. I don't like that. Because this is an expectation. Again, if I've got a t there, it's on this bigger probability space. So when I do that, it looks like I'm going back to my original, the same thing. But, I mean, this t is in a grander probability space. But you see, what I wrote before, I had eta times the mean of t. It's the same as summing eta t times. And that's why I can go and take this minus this. Yeah, it's cute, huh? Yeah, yeah. So yeah, that's it. So done. We've got convergence of value iteration, and it is nice if you can see it. The rate of convergence could depend on moments of t. So if you remember Chebyshev's inequality, if you've got exponential moments on t, you're going to get a geometric rate of convergence. Go back and remember if you've got, not Chebyshev. Chernow's bound, yeah. You've got exponential bound on moments of t, you've got exponential convergence. If you have a second moment, you'll have a 1 over n squared rate of convergence. I mean, go back to your bounds, So we actually know it's geometrically fast. Our spectral theory says that. I mean, we'll exercise. So you actually, and you know that it all has to do with that. Yeah. Okay, cool. All right. So no more questions? You're all incredibly brave, especially you, Jonathan. Next time, I don't know. Take a look at the notes in advance if you have, if you think of.